it's great to be here. I'm Gon. So today I'm going to talk about scaling inference for Gen AI, focusing on optimization techniques and lessons learned. So just a few years ago, Gen AI was mainly a research curiosity. Today it's everywhere, from productivity tools to co-pilots, from creative applications to enterprise workflows. And the rapid rise of powerful open source models also contributed to this transformation, making advanced AI more accessible than ever. But behind every magical product lies a massive computational challenge: inference at scale. So inference is the process of getting an output from a model, which is how your customers interact with your AI product. It's directly correlated to business outcomes at scale. As the AI product scales, inference dominates the economics and user experience. Every single token generated requires GPU cycles. At scale, this adds up to billions of GPU seconds per day. In real-world deployments, inference often accounts for 80 to 90% of an AI model's total lifetime cost. So improving inference is hugely impactful. So companies today face these critical inference constraints: performance, cost, and reliability. If inference is too slow, users churn. If it is too expensive, business models collapse. If it's unreliable, mission-critical applications won't adapt. So that's why scaling inference is the essential enabler for Gen AI to deliver real impact. So the big question is this: how do we design inference systems that are fast, cost-efficient, and reliable, while serving many, many users across diverse workloads? So that's the topic I will dive into today. So let's start with some background. Let me first explain the inference workflows like ChatGPT works, how inference unfolds in these auto-regenerate regressive AI models. In the first step of the inference, the entire input sequence, called prompt, is processed. This is known as the prefill stage. In each subsequent step, the model runtime reuses the cached key and value pairs from all previous tokens and computes them only for the newly generated token. So this process, called the decode stage, uses a key value cache, in short KB cache, which just stores information on all previous tokens to avoid redundant computation. And as you can see, it is iterative. So that is the workload. And this workload runs on GPUs. As you know, GPUs are designed for massively parallel processing, making them well-suited for the large-scale computations required by modern AI models. From a systems perspective, GPU software optimization is all about identifying and addressing bottlenecks within the limits of compute, memory, and bandwidth. Most important dimensions to consider are flops for compute power, bandwidth across storage layers, for example, transfers to and from GPU RAM, and the size of GPU RAM, which directly impacts how much data and how many requests can be handled in parallel. To understand how GPU performance works, we typically use the well-known roofline model. The GPU kernel, which is the code executed on GPUs, can be compute-bound or memory bandwidth-bound, depending on the regime it operates in. And what we want is to fully utilize compute without being limited by memory bandwidth. Now, the last slide for the background. What are the goals we are optimizing for to scale? So we talked about latency, throughput, cost, and reliability. So here are some metrics we can use to track how well we are doing. On the performance side, we care about two key things: low latency and high throughput. For latency specifically, there are two important metrics to track. First, time to first token, TTFT, captures how quickly the model starts responding. So if you are working on voice AI agents, for example, this is very important metric to use. Time per output token, TPOT, captures how fast it generates each additional token. For throughput, tokens per second or requests per second are the metrics we use. And also, what's important is that we would like to improve performance while preserving model quality. So when we apply optimizations, we need to ensure that the model still produces high-quality outputs. Lastly, when we talk about reliability, we care about high uptime, measured in how many nines we can guarantee. So now I'm going to switch gears and start with techniques to optimize performance. To achieve the goals, we apply a range of optimization techniques. Key optimization techniques for inference include batching, quantization, GPU kernel optimization, caching, parallelism, scheduling, speculative decoding, disaggregated serving, and more. It's a lot. And each technique targets different bottlenecks. Some focus on latency, others on throughput, and some improve both. And with friendly inference, you skip the complexity and focus on results. Given the time, I'll walk through some techniques at a high level to highlight the key ideas. So first, throughput. The most important optimization for throughput is batching. As I said, GPUs have many computing cores, but to make full use of them, we need to give the GPU enough work. In inference, GPU operations involve two types of data: model weights shared across all requests, and activations unique to each request. And batching processes multiple requests together, which reduces model weight movement and increases arithmetic intensity. And this helps shift workloads from memory-bound to compute-bound, but it comes at the cost of higher GPU RAM usage, especially for storing the key value cache. In practice, inference traffic is very dynamic and uneven. Requests come in at irregular times, and they don't all take the same amount of time to finish. That's why traditional batching isn't enough. The industry standard for handling this is continuous batching, also known as iteration batching, a technique proposed by Friendly AI. With continuous batching, you can dynamically add new requests to the batch or remove completed ones from the batch at a fine-grained level, keeping the batch efficiently packed. And this allows the system to maintain high GPU utilization even when traffic is dynamic and uneven. And we currently use an even more optimized version of continuous batching in production. If you're interested in the technical details, check out our ORCA paper. It already includes many of the latest ideas in the space. Now, let's take a look at optimizations that affect both throughput and latency. So first, let's start with quantization. So quantization reduces number of bits used in data and computation, improving bandwidth efficiency and flops, but it can affect model quality. There is a range of methods depending on which parts of data and computation are quantized and what formats are used. So for NVIDIA Hopper, there's FP8. For NVIDIA Blackwell, there's FP4. They are the best in terms of performance. But I would like to highlight that just because two companies say we use FP8 or FP4 doesn't mean they are using the same quantization method. Different teams implement it differently. So we have our own quantization method, friendly quantization, that preserves model quality while speeding up execution. The graphs here are performance and accuracy results for Llama 3.18 billion from Artificial Analysis, a third-party benchmark site. As you can see, even for the same model, friendly AI provides higher quality than other service providers like Together and Fireworks, and it's faster. Next, GPU kernel optimization. GPU pipelines are managed primarily at the software level. How efficiently we schedule and coordinate operations has a major impact on performance. Without effective pipelining, only a small fraction of GPU's compute capacity is actually utilized. So to fully leverage GPU hardware, we need to overlap execution across different functional units, such as tensor cores, CUDA cores, and data transfer. And we also have to be careful about how we handle numerical precision in handling dynamic tensor shapes. So flash attention is a great example here. Flash attention carefully restructures attention computation to maximize memory locality and overlap operations, thus improving both speed and efficiency. We have our own friendly kernel library, which is our own optimized kernels for GPUs. Now, next, caching. Caching is essential. For transformer models, we use key-value cache. KB cache stores intermediate combinations of keys and values across iterations for a single request, and also across requests to skip prefills when there is a cache hit. And friendly caching covers more. It supports multimodal data, not just text. Integrates with CPU RAM and NVMe SSD, and optimizes with cache-aware routing. So because of this functionality, multimodal startups like 12 Labs use friendly solutions. Next, parallelism. Parallelism across GPUs improves both latency and throughput. Tensor parallelism is the default when the model is large. For MOE models, expert parallelism can be also used, partitioning experts across GPUs. So in production, there are different configuration choices depending on your MOE model setup, and you can combine tensor parallelism and expert parallelism. So we need to optimally choose the combination based on the model, workload, and GPU type, and it's automatically handled by us. Now, there are techniques that affect latency more. Speculative decoding is the most well-known example. It has been gaining attention to speed up inference in small batch scenarios. Small batch. It generates multiple tokens per forward pass to improve TPOT, helping shift the workload from memory bound to compute bound. In spec decoding, a small draft model is used to propose tokens. Then the original model validates the draft tokens. The key trade-off here is between how many of those draft tokens get accepted and how much compute it takes to generate them. There are a set of draft models people are proposing, and it's quite actively explored at the moment. And for us, we have developed a lightweight spec decoding method with high draft token acceptance rate and low computation complexity. Now, this aggregate serving is the last performance optimization I'm going to talk about. This aggregate serving uses separate GPUs for prefill and decode. And this allows us to scale and control TTFT and TPOT independently. However, it adds GPU to GPU communication and adds more cost and infrastructure complexity. So from our experience, depending on your workload, it can sometimes be worth it, but other times, the cost outweighs the benefit. Now, reliability. But when it comes to mission-critical production applications, nothing matters more than reliability. So there are tons of scenarios to consider. GPU failures. GPUs fail more often than you think. And in particular, scale-up architectures pose greater challenges for failure handling. Let's say you have 72 GPUs in a server and one GPU fails. What do you do? It's quite challenging. Network failures also happen more often than you expect. Microservice failures, database failures, cloud vendor failures. Even major providers can experience outages. For example, the recent Amazon incident, sudden traffic changes, etc. So to address these challenges, we must adapt and put these principles into practice, all of which are already built into Friendly AI. So the first principle is redundancy. Critical components are deployed with built-in redundancy to eliminate single points of failure. Automated fast failover. Proactive monitoring and alerting. Graceful degradation. This one is interesting. In the event of a partial system failure, non-critical features can be temporarily disabled while core functionality remains available. For example, your control plane may be not available for a minute, but your data plane is not affected. Automated recovery, resilience against large-scale outages. Even cloud vendors can fail, so with geo-distributed multi-cloud infrastructure, the inference services remain operational even in the face of large-scale outages. And lastly, intelligent and reliable auto-scaling. Rapid, reliable auto-scaling handles sudden traffic spikes, ensuring stable and predictable service. So that's a lot. If you don't want to deal with all that, Friendly AI is for you. So Friendly Inference is our purpose-built inference stack for speed, scale, cost efficiency, and reliability. At the core of Friendly Inference is our custom inference engine. It is purpose-built to run AI faster and more efficient. It brings together years of innovation to power both language and multimodal models through a single unified engine. At the infra level, we support all these features for reliability, performance, and usability. Intelligent routing for maximizing performance, auto-scaling for scaling quickly for traffic changes, real-time enterprise-grade monitoring like tokens process, latency, etc., live model updates and model versioning without service disruption, and online quantization and spec coding. So you don't need to run offline steps to use quantization, for example. Tool cores and reasoning, 99.99% availability, and geo-distributed infrastructure with multi-cloud vendors. And lastly, the integration with Hugging Face and weights and biases. So why Friendly Inference? First, it's quick to market with extensive model support, including over 460K open source models from Hugging Face. And if a model isn't supported yet, just contact us. We'll work with you to make it happen. Second, it's fast. For example, our platform supports over 100 tokens per second for Qwen 3 to 35 billion on Hopper GPUs. This is, again, faster than other service providers like Fireworks and Together. Third, it is cost efficient. If you're using, let's say, LLM or SGLang, we are delivering more than 2x the throughput of those solutions. So you can enjoy this benefit with the latest, even MOE models as well. And finally, it's reliable at scale. Right now, we are supporting trillions of tokens processed with 99.99% availability. So you can run AI models of your choice on our platform, friendly endpoints, or you can even deploy models directly from Hugging Face on our platform with a few clicks. So I hope that it's working.
Now you can easily deploy models directly from Hugging Face Hub with friendly endpoints. Just go to Deploy Options on Hugging Face model page and select friendly endpoints. It's that simple. You can deploy a model with just one click. Once the deployment is complete, head over to the Friendly Suite to access even more powerful features. Now you can enjoy the fastest and cost-effective inference with Friendly AI's GPU-optimized inference engine.
Okay, right, so it's so simple. You can try out your models of interest. Once it's deployed, you can use APIs to call the models for your agents or chatbots. We also have a solution for companies with strict security or privacy requirements. So it's called Friendly Container, our high-performance self-hosted AI inference solution. And if you're on AWS, Friendly Container is also available as an EKS add-on. So just run a single command to install and integrate it into your existing AWS EKS workflow. So let me share some of the testimonials from our clients. Our clients are very happy with our platform and switched from other providers to us. So for example, LG has their own foundation model called XR1, and we're the API provider, only API provider of their XR1 model. They really like our platform speed, quick time to market, and our support. Upstage is another example. Upstage is a startup providing services like document understanding using their Solar foundation model. The models run on Friendly AI. They are again happy with reliability, speed, cost reduction, and quick time to market of Friendly. Okay, so with that, wrapping up, AI inference is critical. Latency, throughput, cost, and reliability all matter. We talked about performance optimization and reliability of AI inference. Friendly AI offers a purpose-built platform engineered for speed, efficiency, scalability, and reliability. So you can focus on building great AI products. It can be agents or chatbots or customer supports while we handle the complexity of inference. One more thing, we have the Friendly AI 10K Gen AI Inference Credit Program. If you are scaling your AI and would like to try out our platform, you may be eligible for up to 10K in free inference credits. So scan the QR code to apply. It's simple, it only takes 2 minutes. Thank you. I'm happy to take any questions if time. I'll also be around after the session. Feel free to come chat if you have any questions. Thank you.
So I see that you have like a Hugging Face integration, but like, let's say I want to fine tune my own model and then deploy it. So what's the approach? Do you provide an SDK or how does that work?
So after deploying it, you can just use REST API. So there are some code examples, or you can use our SDK, or you can use OpenAI SDK.